We know that when a light ray passes from denser to rarer medium, it partially refracts to the rarer medium and bends away from the normal, and partially reflects back into the denser medium. This reflection is known as the internal reflection. In case of refraction from denser to rarer medium, the angle of refraction R is greater than the angle of incidence I. If another light ray with higher angle of incidence is considered, its angle of refraction will also be correspondingly higher. If the angle of incidence of the light ray is gradually increased, then for a specific angle of incidence, when the angle of refraction in the rarer medium becomes 90 degrees, the refracted light grazes along the interface. This angle of incidence in the denser medium is called the critical angle C for the pair of media under consideration. That means if I is equal to C, then R is equal to 90 degrees. Let N21 be the refractive index of the rarer medium with respect to the denser medium. Let N12 be the refractive index of the denser medium with respect to the rarer medium. We know that N12 is equal to 1 by N21. As per Snell's law, N21 is equal to sin I by sin R, which is equal to sin C by sin 90. Therefore, N21 is equal to sin C, or N12 is equal to 1 by sin C. This means the refractive index of the denser medium with respect to rarer medium N12 is equal to 1 by sin C. If the angle of incidence is made larger than the critical angle, the incident light cannot refract to the rarer medium and is completely reflected back into the denser medium. This is known as total internal reflection. Since there is no transmission of light to rarer medium, light gets completely reflected back to the denser medium. That is, it gets totally internally reflected. Hence, for light to have total internal reflection, it must satisfy the following conditions. 1. It must propagate from denser medium to rarer medium, and 2. The angle of incidence must be greater than the critical angle for the pair of media. Observe how light refracts through a glass-air interface for various possible angles of incidence. Let us look at some examples and applications of total internal reflection. Formation of mirage and the sparkling of a diamond is due to total internal reflection. The illusion of the presence of water on a hot summer day at a distance is known as mirage. The images of the nearby objects give the impression that there is a pool of water, but this in reality is an optical illusion. During a hot summer day, the layer of air nearest to the surface of the earth is hottest. And as we move up the ground, we come across layers of air with decreasing temperature. As a result, the refractive index of different layers of air increases as we move up. And hence, layers of the hot air near the Earth's surface are optically rarer than the layers of the cold air a little above it. Due to this, rays from the nearby objects which are propagating towards the Earth's surface refract and bend away from the normal. At some point, the angle of incidence exceeds the critical angle and the rays undergo total internal reflection. An observer is able to see the image and get the impression of a mirage. Another example of total internal reflection is the sparkling of diamond. Diamond has a high refractive index of 2.42 and the critical angle for the diamond-air interface is 24.4 degrees. Diamonds are cut in such a way that most of the light rays entering the diamond undergo total internal reflection many times before they exit. This gives diamonds their bright sparkle. Total internal reflection is made use of in some technological applications also. In many optical instruments, prisms are used to deflect and redirect the light without loss of intensity. Right-angled prisms are most commonly used for such applications. A right-angled prism, whose critical angle is less than 45 degrees, can be used to deflect light at a right angle. Light incident normally on side AB passes without deviation and incident on side AC at an angle 45 degrees. Since the angle of incidence is greater than the critical angle, the light is totally internally reflected and is deviated from its original path by 90 degrees. If light is incident normally on the side AC, it travels straight and hits side AB. Then, light is internally reflected twice at surface AB and BC and leaves the prism with a deviation of 180 degrees. In this case, the image of an object gets inverted. The same prism can also be used to obtain an inverted image of an object without changing its size. Another application of total internal reflection is in optical fibers. Optical fiber is usually fabricated from glass or quartz and consists of core and cladding. The refractive index of the core material is a little higher than that of cladding material. When light is allowed to enter the core in such a way that the angle of incidence at the core cladding interface is greater than the critical angle, it will undergo successive total internal reflections all along its path in the core. Since the loss of energy is quite small in case of total internal reflection, light can be transmitted over longer distances through optical fiber with least loss of energy. This is made use of in case of optical fiber cables used for long-distance transmission of light signals. In communication systems, optical fiber cables are used to transmit video and audio signals at the speed of light. In such cases, the electrical signals are first converted to light signals and then they are transmitted through optical fiber cables. Optical fiber has applications in medicine also. It is used by doctors to illuminate and view the internal organs such as the esophagus, stomach, intestines, etc. to get back their images and if necessary to even carry a laser beam to the relevant spot.